Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, everyone. This is the second part of optimization problems, which involve maximum and minimum. Okay, as discussed in part 1, these are the 5 steps to solve optimization problems. Number 1, find an equation to maximize or minimize. This is called optimization equation. Number 2, reduce this equation to one variable only. Sometimes you might have optimization equation in just one unknown variable. So in this case, you can just go ahead and do step 3 here. Okay, step 3 is find critical values. This one you have to set the first derivative to 0. The step number 4 is verify the critical values that you get, whether they are maximum or minimum. This one you have to use the second derivative test. And last one is answer the question being asked. Now, keep in mind that all optimization problems can be solved using the same steps here or methods. Okay, even though the story of the problem might be different. Example 2. This example is taken from your DM025 note. Okay. An open box with a square base is to be made from a square piece of cardboard that measures 12 centimeters on each side. A square will be cut out from each corner of the cardboard and the sides will be turned up to form a box. Find the dimensions that yield the maximum volume of the box. Okay, now this is a 12 by 12 centimeter piece of cardboard and we want to cut out this square, alright, these squares from each corner here. And fold up the sides, this one, this one, this one, this one, fold up these sides and form this box where the top is open. Okay, now each of the corners here is an unknown length, so we put x here. Okay, we can call that x. So we'll put x here. This one is x, this is x. So this one is x, this is x, that is x, this is x, that is x. This is also x. Okay, we want to find the dimension of this x that we need to cut out. If you cut out a lot of x, let's say this is your x, alright, if you cut out a lot like this, okay, you will have a tall and thin box. Okay, tall and thin box, something like that. Okay, but if you cut out very little x, let's say this is your x, very little, okay, this one, okay, that one, and this one, very little x. Okay, this one, you will have a flat box like this. Okay, something like that. So how much should we cut out this x to maximize the volume of this box? So step number 1 is to get the equation of the volume. That is the optimization equation. The volume of the box is V, that is equal to the length multiplied by the width multiplied the height. What is length, width, and height? So now, if we fold up this side, okay, this edge, right, the height of the box here would be x centimeter. Okay, this one is x. This length here, this dotted line, alright, would be the length of this edge. Okay, so this length would be 12 minus x minus x. So the length of this edge is 12 minus 2x. Okay, now this length here, the dotted line here, would be the length of this edge. Alright, so this length would be 12 minus x here minus x here. So the length of this edge would be 12 minus 2x. Okay, now we get the volume of the box, that is the length is 12 minus 2x, the width is 12 minus 2x, and the height is equal to x. if you simplify this or expand this, you will get 144x minus 48x squared plus 4x cubed. So that is the volume of the box. That is step 1. Now step 2 is to reduce this equation into one variable. So if you notice here, this v is in terms of one variable, that is x. So you do not need to do anything in step 2. You can go ahead. This one is done. You can go ahead to step number 3. What is step number 3? Step number 3 is to find the derivative of v and set it equal to 0 because we want to find the critical values. Okay, so now the first derivative, that is v prime, that is equal to 144 minus 96x plus 12x squared. Okay, set that equal to 0. Then you can divide each term by 12 and you will get 12 minus 8x and then minus x squared. Okay, that is equal to 0. Factorize that one, you will get x minus 6 and x minus 2, equate that to 0. Then if you solve this, you will get x is equal to 6 and x is equal to 2. Now these two are called the critical values. Okay, these critical values. Okay, now we have two critical values here. One of these values will give the maximum volume. So we need to pick one. How? By using the second derivative test. So we go to step number 4, that is finding the second derivative test. Our second derivative here is v double prime. That is equal to from here, that is minus 96, alright, plus 24x, that is the second derivative. Now you plug in the critical value. In this case, x is equal to 6. Okay, when you plug in the second derivative, you will get minus 96 plus 24 multiplied by 6, and this is equal to 48, and this is greater than 0. So when this is greater than 0, you can conclude that x equals 6 will produce or will give the minimum volume. This is a local minimum, okay? Minimum volume. Okay, now another critical value is x equals 2. Plug in this critical value in the second derivative, you will get minus 96 plus 24 multiplied by 2, and here you will get minus 48, and this is a value that is less than 0. Okay, you get a negative number here. So since you get a negative number here in the second derivative, this means that x equals 2 here corresponds to a local maximum. Therefore, you can conclude that x equals 2 will give maximum volume. Okay, now we go to the last step, that is step number 5. Step number 5 is to find or to answer the question being asked. What is the question? Find the dimensions that yield the maximum volume of the box. So the dimension here is, first is the height. The height is x. X is equal to 2 centimeters here. Okay, the length is 12 minus 2x, and that would be 12 minus 2 multiplied by 2, that is 12 minus 4, so that is equal to 8 centimeters. And the width, okay, so this is 12 minus 2x as well, so that is 12 minus 2 multiplied by 2, and you get 8 centimeters. So these are the dimensions, alright, the length, the width, and the height. These are the dimensions of the box that will give the maximum volume. Okay, so this is the end of part 2. Watch my video for part 3 of the optimization problem. Okay.